we discussed examples on how a binary search tree might just become ill-balanced after certain insertions. In fact, not just insertions but also deletions can cause the tree to be ill-balanced. As long as you're trying to modify the structure of the tree, either to add a nodes or remove a nodes, you have to be careful. After the updates, if the tree becomes ill-balanced, meaning that the high balance property is compromised, you must do something. And a very common practice is about doing rotations. And before we actually do some very concrete exercises together, I got quite a good number of exercises to do with you. Before that, I would like to give you some abstract introduction or intuitive introduction to what a rotation is. Let's take a look. A tree rotation will be performed if the latest insertion or deletion creates unbalanced nodes. And don't forget, the insight we actually concluded from the earlier part. We said that those unbalanced nodes should be along the ancestor path of the node being inserted or deleted. Let me go back here. Remember the insight we made before? The ancestor path of the node being inserted, some of the nodes towards the root was actually have become unbalanced. That's really what I meant over here. And given that some nodes along the ancestor path become unbalanced, what we should do is using rotation to change the shape of the tree without changing its contents. Just remember that whenever you do rotation, the same tree is still there by just kind of changing the way you organize the parent and child nodes. We'll see that exactly. And we want to restore the high balance property. That's the most important part. We want to restore the balance property. However, it is okay to really change the structure of the tree as long as all the entries are still there. This will be just one possible case of performing the rotation. It's so-called performing a right rotation on certain nodes. Let me just give you some intuition on this and maybe point out exactly what's really important when you do the rotation and what's really the arguments that it will be okay to really change that organization while maintaining the contents of the tree. Let's take a look. Okay, over here, so this will be the tree. Right, so we are trying to talk more at the abstract level. You can see we got concrete nodes A, B, and C. Presumably, if you try to do the in-order traversal, it should be C followed by B followed by A. Right? Of course, I'll talk about the subtree as well in the in-order traversal in just a moment. Let's make the following assumption. Let's say the height of this tree over here, of course, the height of this node over here is H, and similarly for this height, also H. Accordingly, the height for the root of these two subtrees will be h plus 1. And then we got, let's say, T3 and also T4 also are of heights h. Accordingly, the heights for this node will be the maximum of h plus 1 and h, which will be h plus 1 and then plus 1. So that's why you got h plus 2. And the height for this node over here will be the maximum amount h and h plus 2, which will be h plus 2 and then plus 1. You got h plus 1 for the height of this node. Right, so that's the tree we have. Of course, this is only just one example tree. In when we do the exercises, you might see other shape of the tree as well. We'll see. Two questions for us to go over quickly. Is the above tree balanced? That's a very important question. And in order to check it, you want to check for every internal nodes for their heights of their two children. Let's now take a look. For example, for this node over here, is it balanced? Indeed, it is. Because if you look at the heights for the two children over here, the subtree T1 and T2, the difference over here is simply 0. H minus H will just be 0. What about this node over here? Is it balanced? Is node B balanced? In this case, yes. Because if you look at the two child nodes over here, this part over here, you can see the heights will be H plus 1 and H. So the difference is actually 1. So that's still fine. What about the node A over here? Is it balanced? It turns out it is not balanced because if you try to look at the two child nodes over here, so this will be the points where it is not balanced. Let me use a different color. If you try to look at this child nodes of A over here, you can see we got H and then we got H plus 2. So the difference is actually 2, which is strictly larger than 1. So this is where we can see the A is not balanced. So you can see A over here is actually not balanced or unbalanced. So that'll be the answer for the first question, but you should really understand exactly how to compare or to check the whether or not a node is actually balanced or not. And the second question, after a right rotation on node B, is the resulting tree still a BST? Let's now just do some pre-processing job before we actually do the rotation, which I can show to you. The way to judge whether or not we are compromising the search property of the tree is by looking at the in-order traversal. Let's take a look. Before the rotation, what about the if we do some in-order traversal on the tree? In-order traversal. What's going to be the order? Well, if you do the in-order traversal, it's going to be T1, and then C, and then T2, and then B, and then T3, and then A, and then T4. Agree? So by now, you should be very familiar with the in-order traversal. Let me write it down. It's going to be this particular sequence. T1, followed by C, followed by T2, followed by B, followed by T3, followed by A, followed by T4. And we know that this is really the unbalanced node. So it would be nice to somehow change it so that it will become balanced. Specifically, we want to somehow adjust the heights of its child nodes over here so that they will become the difference between them wouldn't be larger than or equal to 1. It wouldn't be larger than 1, strictly speaking. The idea would be we want to do a rotation on the middle node over here. Whether we should really do a rotation on the middle nodes or lower node, there will be some cases for us to consider. But for this, at this moment, we don't need to worry about the cases. Let's say, take it for granted. In order to fix the balance, we have to do a rotation on this middle node over here. That's what we're going to do. Okay, let me write it down here. So what we'll do is we're going to do a rotation. Rotates the middle node B to the right. And the reason that we say it's a rotation to the right is, think about, we're going to somehow imagine we're going to rotate in this way as opposed to this way. Okay, so we're going to rotate B to the right. In that case, we're going to promote B to be the new root. Okay, so what we're going to have is B is actually going to become the root of the tree over here. This will be B. So this will be the new root of the tree. Everything else should be done in a way that would be consistent with the in-order traversal, because we know that before B, what comes before that will be T1, C, and T2. Right? You can see this should be the right subtree. T1, C, if I can maybe use a highlighter over here. T1, C, and T2. And after B will be T3, A, and T4. We should really maintain that particular order. So what we should do is we can say the left child over here and also the right child over here. The in-order traversal for the left subtree should be T1, C, and T2. That will be easy. In that case, it will just be T1, C, and T2, just that structure. So you can think about this entire subtree is just going to be now connected to as a left subtree of B. Let's now do that. So that will be, we got C over here, and then we're going to have T1 and T2. And at the same time, let's now also work out the heights in just a moment. Okay, so this will be T1 over here, and this part over here will just be T2. T1 and T2. Let's annotate the height right away for these for this half. T1 and T2 haven't been changed, so height remain to be H. What about C? Maximum of H will be H plus 1, H plus 1. So you can see here, we have the height for C, this part over here remains unchanged. But let's now see what's going to happen for this particular part over here. That'll be A followed by T3 followed by T4, right? Beg your pardon, it should be T3 followed by A followed by T4. T3 followed by A followed by T4. That should be the in order. And the way to do that would be we're going to do, let's say over here, we're going to have T3 after that followed by A and followed by T4 over here. Okay, so T3 and also T4. And let me just get this part done better. Not exactly perfect, but hopefully that's acceptable to you. All right, so we got this, and let's now take a look at the heights over here. T3 and T4 hasn't really been changed, so remain to be H. And then what about A? A will be the maximum amount H and H, which will be H plus 1. Okay, just a little bit picky over here. Why don't we just draw this a little bit better? There we go. Okay. Finally, what will be the heights for B over here? Maximum amount H plus 1 and H plus 1. That should be H plus 2. Is this resulting tree balanced? First of all, there are two things we got to check. One thing is about whether or not it's balanced. Number two, have we lost any contents? The same content for the tree? And number three, is it still a BST? So these are the three things we would like to find out. Right? If these three things are all satisfied, that means the rotation is valid. It's magical. Number one, is it balanced? Indeed. Because now if you try to look at this part over here, the C over here is balanced because H and H, the difference is simply just 0. Symmetrically, for node A is also balanced because H and H, D is actually 0 difference. What about node B? Used to be EO balanced, used to be, right? And if you try to look at these two over here, the difference between H plus 1 and H plus 1 is 0. So awesome. So now we don't have any node that's EO balanced. So this tree over here will be, you can think about this tree that's been after the rotation is balanced because for every internal nodes, their channel's heights differ no more than 1. That's it by definition. So the first question here, check. What about, are they the same contents? Indeed. We got T1, T2, T3, T4, T1, T2, T3, T4. We also got CBA. We also got CBA, even though they have been rearranged a bit, but all the contents are there. So it's more like a permutation in some way. Finally, is it still a BST? The way to check it would be to see the in-order traversal. So let's say after, let me put it down over here. After the rotation, I want to do this explicitly just to show you the point. It's really important to judge whether or not the rotation is actually valid. We got in-order traversal. In-order traversal is going to become, let's see, how's it going to happen? T1, C, T2, B, and then T3, A, T4. Agree? That should be T1, followed by C, followed by T2. And then the B, and then T3, followed by A, followed by T4. That'll be the in-order traversal. If you compare these two over here, they're exactly the same. The same, right? It's really important to make that explicit point to say before the rotation and after the rotation, they stay the same. Before the rotation and also after the rotation, the in-order traversal really stay the same. Okay, over here, the same. This is why this is still a binary search tree. Also checked. These are the three questions you always ask yourself whenever you want to perform some rotation on the tree with the purpose of restoring the balance. Make sure the resulting tree, of course, it should be balanced. Otherwise, why would you do it? Should be balanced, and also the contents will not be lost, and also the search property is not compromised. Right? If you compromise this property, even though the tree is balanced, but it cannot be used for search purpose anymore. Let's now go back to see if there's anything else. Right, so that's everything I have covered on the iPad. You can definitely also try to look at the bullet points over here that just give you a little bit more detailed comparison between the before and after, but you definitely get an idea.